Hey everyone, welcome to our New Year's first meetup with Pittsburgh.NET user group, and it's part of the .NET Foundation. And we'll get started. So Pittsburgh.NET user group is part of the .NET Foundation. We have close to 1,000 members, and we also do meetups regularly every month, and we do put it as a part of the virtual .NET user group as well, so much better audience. So today we are going to look into the intro to Hastlayer, and I will introduce Zoltán. Hey Zoltán, welcome to the group.
Hello, hi everyone.
I will try to have this one. Yep, most of one screen I was searching for. Thank you, Zoltán, for joining us today, and I'll let you get started and introduce yourself, and we'll get started with the session. Thanks everyone for joining us today.
All right, great. Thank you. And yeah, it's great to be back because sometime in the first half of last year, I believe, I already gave a talk here about the .NET Core and .NET, and now ASP.NET Core, CMS and web framework called Orchid Core. And now I'm back with something completely different, except for this thing being something related to .NET as well. And why I wanted to give this talk at this meetup too is because as .NET developers, perhaps you only think of yourself as somebody who can create software. But actually, you can also create hardware with your .NET knowledge. And this is what our Hastlayer project allows you to do. But before going any further here, a little bit of introduction about me and where I'm coming from. So I'm Zoltán Leoczki. I'm from a company called Lombik Technologies. And day to day, we are actually doing Orchid Core development and consulting, training, everything with it. And when we are not doing Orchid Core development, then we are doing some research and development. And among these projects are also web and usual .NET projects and some cutting-edge R&D projects like Hastlayer. But before going any further with Hastlayer itself, let's talk a little bit about you. Now, let's suppose that you are doing some number crunching. And by number crunching, I mean that you work on some kind of software that's in the field of AI, or more specifically machine learning, including large language models, which are quite fashionable today. Or your software is doing something perhaps with images or videos, perhaps in an embedded system like a robot, where it's more about computer vision. Or perhaps you work in finance and your software is doing some algorithmic trading on the stock market. And there, every microsecond counts. We are talking really about microseconds, where in .NET usually we think in terms of milliseconds at most. Or your app does something with a lot of data, and you need data compression for storage, for transfer, something like that. Or perhaps you are doing something in the sphere of cryptocurrencies or cryptography. Now, when you are doing these things, then perhaps you want to make your application faster. Perhaps it's fast enough, but it's in some cases it can never be fast enough, or it's downright slow. People are complaining, or it just uses too much resources. So you want to reduce the resource consumption to make operating the software cheaper. And there are a couple of steps you can take to solve this issue. And first of all, of course, you can figure out what's slow, what takes the most resources. And the way to do that is to profile your application and then optimize it. Let's suppose that you have already done that. And a further step, or sometimes the part of optimization is to parallelize your algorithm. Now, we are talking about still parallelization, what happens in your application. So you're pretty much using the task parallel library to start tasks, which are like bigger chunks of parallelization, or you can use the quite recent or the very recent new .NET APIs for single instruction, multiple data parallelization, also called vectorization. Or you can use some other APIs to parallelize the algorithm inside your application. So pretty much utilize all the hardware that you have in your machine, be that machine something local or something in the cloud. Let's suppose that you have done that as well. And the last step is pretty much throwing money at the problem. Now, if you start with a money problem because you want to reduce resource consumption, then that's less of an option. But otherwise, you can always use faster hardware, scale up, or use more hardware, scale out. In the cloud, both of these are quite simple, or otherwise you can rent hardware, pretty beefy ones. So that's also an option. Let's suppose that you have exhausted that option too, or it's not feasible enough because, at one point, even if you have a lot of money, throwing money at a problem becomes a problem in itself. Now, what else can you do? Well, you can turn to heterogeneous computing approaches. Now, even if you don't know this term, I'm pretty sure that everyone here somehow utilized it because, for example, using GPUs, video cards, is a form of heterogeneous computing. It just means that you use more than one processor, more than one kind of processor to do the computations for your app. So while you still have a CPU, some specialized computations can be offloaded to some specialized processor. And GPUs are like that, but also you can utilize some magical devices for this use case called FPGAs. And let's talk about FPGAs a little bit more. If you haven't heard of FPGAs before, don't feel bad. That's a super low-level thing and not something that software developers usually work with. Although if you have some formal education, possibly something with FPGAs was part of the curriculum, because FPGAs, or field programmable gate arrays, are computer chips that can pretty much behave like any other computer chip, within some size limitations, of course. So this means that if you have an FPGA, you can configure it to, for example, recognize like cat pictures. Or you can also change its configuration to make it compute some physics calculations. It's completely reconfigurable. It can be any processor you want, but of course it has a capacity within what will fit on that chip. And if you Google something on Bing, as they say, then, well, you have used FPGAs because it is accelerated by FPGAs too. Or if you run anything on Azure, same thing, because Azure uses FPGAs for networking, to accelerate networking. But FPGAs are sometimes also can be found in household appliances like routers, or less household appliances like X-ray and MRI machines. And they are also sometimes part of the processing unit of self-driving vehicles. The thing that you have to keep in mind here is that you have to be a hardware engineer to utilize FPGAs because, well, it's about designing a piece of logic hardware. Now, why would we use FPGAs as .NET developers? And the answer here is that FPGAs have some unique computing benefits. We can also utilize them as compute accelerators, much like GPUs. So let's compare them with CPUs and GPUs here, and let's see where their advantage is. Let's talk about parallelism first. So how many things you can compute at the same time on a given processor. And CPUs are pretty much on the lower end here because on a CPU you can have something like 8, 16, 32, 64 cores, perhaps a little bit more than 100, but that's about it. Whereas with GPUs, you have cores in the order of magnitude of thousands. Of course, those are very different cores, but still the level of parallelization you get on a GPU is thousands. And FPGAs are kind of in between here, although you can't really have cores on an FPGA, so to say, although that's not true for every FPGA, but still the level of parallelism you can get from an FPGA is roughly in the order of hundreds, highly depending on your algorithm and on the FPGA, of course. Now, what about the complexity of programs you can run in these devices? Because, you know, when it's a piece of software, a CPU can run it. So CPUs been here, they can then just do anything. They are generic and all-purpose. Whereas CPUs are, again, on the other end, but on the lower end here, because the programming model on a CPU is very limited. Sorry, a GPU is very limited. GPUs are for, well, graphics processing. So what they can compute is specific to graphics calculations. And so you can't just run any software on a GPU. With FPGAs, again, it's kind of in between because although you won't really run a program on an FPGA, but rather you turn your program into a piece of logic hardware with an FPGA, the level of complexity you can achieve there is roughly in between, again, highly depending on a lot of factors. And lastly, power efficiency. So how much can you compute with 1 watt of power? And FPGAs win here because FPGAs are very power efficient devices. CPUs and GPUs are generic to different degrees. They meant to be programmed, whereas an FPGA, I mean, they meant to run just any program compatible with their platform. But an FPGA only computes what you need to be computed. It only does what your algorithm needs. And because of that, there's nothing unnecessary. There's no operating system to run, and no instruction set even, like with any processor. It's just bare metal. But there's a downside, and I already hinted on that. You have to be a hardware engineer to use an FPGA because it's hardware development. And then if you are coming from a software background, like I would assume most people here, it's a very different world. You have to think in terms of logic gates and wires and clock cycles. It's super low level. It can be fun if you like these kind of things, but still it's super low level. But what we aim to achieve with tools like Hastlayer is to bring this complexity down all the way to the software development level. Speaking of which, what I'm actually talking about here, Hastlayer is a tool that takes a computer program and turns it into an equivalent FPGA logic. Or we could also say that it takes a computer program and turns it into a computer chip. That's kind of one of our taglines too. And what actually happens here is that there's some logic in a software. There's some algorithmic logic. Hastlayer tries to get that out of the software and create some equivalent hardware logic. And of course, we are not talking about just any software. We are at a .NET meetup, so we are talking about .NET software. And actually .NET. So this is not a euphemism for C#, because Hastlayer processes the .NET assemblies. It decompiles the .NET DLLs, and because of that, at least in theory, any .NET compatible language can be used. We have C# and F# samples, but I'm pretty sure Visual Basic shouldn't have any issues either. And we can even test scripting languages. And Hastlayer itself is also a .NET software. Now, to summarize this, why you would use FPGAs is to get the performance benefits of them when you have some highly parallelized, compute-bound and or memory-bound algorithm, because then FPGAs can provide you with a substantial performance increase. I will also show you an example of that. At the same time, you can get a higher power efficiency, so your software will consume less power. And of course, that may sound nice already, but where the rubber meets the road is that less power means, of course, less operational costs, because you are always paying for power twice. You are paying for the power directly that your applications consume when run on the servers, and secondly, you pay for dissipating that power to chill the data center for air conditioning. And all of this is still software development as usual, so not much new to learn. Well, a lot of talk until now, so let me show you some hands-on demo. And I will now switch over to Visual Studio. And what I'm showing you here comes from the Hastlayer SDK, which is up on GitHub. So if you would like to check out the code in detail and check out all the other code, including all the other samples, I will show you a link to that at the end of the talk. But what I'm showing you here now is one of our examples, and probably the simplest one, called parallel algorithm. And you might not have guessed, but this is an algorithm that is highly parallelized. And indeed, if we scroll down a little bit, here is pretty much where the magic happens. This is nothing useful and not a real-world example. This is kind of an exaggerated example of the kind of algorithms that are especially suited to be accelerated with FPGAs and with Hastlayer. So it's kind of a template, if you will. Now, what happens here is that, there's some conditional logic, which is executed 10 million times in a for loop, and then the whole thing is wrapped into tasks. So we execute this mock logic here in tasks. Now, I guess everybody is more or less familiar with the task parallel library and the concept of tasks here, but if by chance not, then you can think of tasks as an abstraction over threads here. And we are starting this many tasks at the same time, and this many is 260. So when our algorithm starts, .NET will start parallel threads for this logic in here, up to the point of having 260 of them at the same time. Well, that will be the maximum, but it depends on your hardware how many threads actually will run at the same time. And at the core of it, you will get as many threads, as many cores your processor have, including hyper-thread cores. So the hardware level parallelism you get on a CPU is again something like 816/32 usually. Now, why we are starting 260 tasks here is because on the hardware we can actually utilize that many. Because when Hastlayer processes this code, it will take a look at this loop here where we start the tasks and figure out that this is actually something that you can completely parallelize on the hardware. And it will create 260 little processor cores that which just compute what you see here. So let's actually see it in action. And what I will show you now to make it more interesting is something that can also go into space. This here, what you see on the camera, is the same kind of hardware that also serves as the onboard computer of satellites, of small satellites. It's a little computer that has an ARM CPU, a 2-core ARM CPU, which is packaged together with an FPGA. So this is an CPU plus an FPGA plus some peripherals. And because of this, this can also run Linux as usual and .NET as usual. So I will now connect to it via a console, and I have it here. What I will do now is that I will run a little demo application on it, which will first execute the previously shown parallel algorithm as software on that 2-core ARM CPU, which just started. And then it will execute it in its hardware form. Now, while I'm showing you this here, because I think this is cool that you can also run your apps in a hardware-accelerated way on an onboard computer, but this is all possible to do on-premises and in the cloud as well. When you go to Azure, you can rent virtual machines that have hardware that Hastlayer can utilize. Now, the demo finished, so let's check out the numbers. Let's see first the software execution, and we can see that on the CPU it took around 25 seconds, give or take. So yeah, this looks like a complex algorithm. Now let's take a look at how much it took on the hardware. So this was executed 3 times on the hardware, just so we can also see some difference there. And here's the first execution. And as you can see, it took around 240 milliseconds on the hardware itself, and around 300 milliseconds together with the whole communication round trip between the CPU and the FPGA. So the hardware execution was about 100 times faster. Now, the hardware execution is just the time that it takes on the FPGA. And take a look at it. It's 240.00456 blah, blah, blah milliseconds. Let's check out the second execution, which is here. And the hardware time is exactly the same. Well, probably at the very end, you will see some other numbers, but it's the runtime is will always be the same down to microseconds. That's actually one of the advantages of using such hardware execution, is that your execution time is reliably exactly the same. Well, if you compute the same thing, so with the same inputs, it will take the same amount of time. And again, this is because on the FPGA, nothing else is running. It's just your logic hardwired into the hardware. There's no other software running there. There's no software running there at all. It's just pure bare metal. And the total, so together with the communication round trip within the FPGA and CPU, took around 260 milliseconds. You remember that the first one took around 310 milliseconds. This is much faster, the second one, because we are talking about .NET. So there was some just-in-time compilation happening. Caches weren't warmed up. The first time is also always a bit slower, and then after that, you can get reliably faster. But still, this is still 2 orders of magnitude faster than the software execution. And this shows you kind of what's possible with Hastlayer, how with some minimal work you can make your application even 100 times faster. Well, at least the highly parallelized algorithmic part of it. And how you would utilize Hastlayer is actually as follows. Because until now, I only showed you parallel algorithm, which is the algorithmic part of this whole thing. But you also have to launch Hastlayer somewhere. And this program example here shows you exactly that. Because this here is how you would integrate Hastlayer into an existing application and use it to offload specific computations. And how it works is that, well, first you create a Hastlayer shell, and then you do some configuration. This is mostly some boilerplate, but it does depend on your application. You first have to select which FPGA you have, And then you have to tell Hastlayer where its computations will start. Kind of like what will be the program class that has your main method in it. We support more than one such class and more than one such entry point, but you have to tell Hastlayer about them. In which case, in the current case, it is parallel algorithm. Then there's also some other configuration to have some debugging output, but it's not important. What's important though is this next line here, this generate hardware async, because this is where the magic happens. This is where Hastlayer takes your code and turns it into an equivalent hardware logic. You also have to pass in the references to the assemblies that your algorithm uses here. If your algorithm is just a single class in a single assembly, then you have to pass in its assembly. But otherwise, you also need to pass in the assemblies that it depends on. And by the way, the .NET Standard Library is also possible to use here. Well, not everything there, because not everything is compatible with Hastlayer. Not every C# is compatible with Hastlayer, but there are parts in .NET that are compatible without any modification. And once you have everything set up, then comes the execution itself. And yeah, pretty much here are the executions, the 3 executions. You see parallel algorithm.run, the same run method that we have seen before. And what's special here is that, well, it's nothing really special, right? Because there's an object and you just call the run method here. Well, why this works is because we have this generate proxy async before it. This is where you pass an object of your algorithm to Hastlayer, and then Hastlayer will wrap it into a dynamic proxy. This allows it to hijack method calls and offload them onto the FPGA. And this hijacking happens dynamically, by the way. So this is not with code generators, but this is with a dynamic proxy. And this has the advantage that you can also decide on the fly whether something should go to the FPGA or should be executed on the host PC. This is important because there's always some overhead to the FPGA computation. It will always there will always be a latency of going outside of the CPU and going to the FPGA, which is, by the way, connected via PCI Express bus. So going to the FPGA only makes sense if you are doing some computation that takes a lot of time. And like this, you can dynamically decide whether something is suitable to be offloaded to the FPGA based on the inputs. Pretty much.
Zoltán, there is a question there if you want
to. Yeah, well, let's do that.
Is it feasible to make PowerShell FPGA?
Well, my short answer or my gut answer would be no, because usually when you are doing something in PowerShell, then it's all about interacting with resources on the computer, like starting other processes, reading files, showing something to the user. That's not something that you would use Hastlayer for. It doesn't make sense. There's no UI on an FPGA, for example. And well, there are no other processes either. So when you are using PowerShell kind of like such a glue to orchestrate a lot of things, I don't think it would make sense to try to accelerate it, because PowerShell itself is not taking too much time. It's rather what you use from PowerShell that may take time, and hardware acceleration is perhaps interesting there. That being said, you can use .NET types from PowerShell. So you can use a Hastlayer accelerated application from a PowerShell script at least. Yeah. So this is how you would use Hastlayer. Now, perhaps you're wondering, okay, but how is the sausage made? I understand how to use Hastlayer. Perhaps I also have a hunch about when to use Hastlayer, but what's Hastlayer doing and how? Now, we can take a peek under the hood here. But again, Hastlayer is up on GitHub. It's fully open source. If you are interested in such low-level things, including compilers, because what's happening here is kind of a compilation process too, then check out the full source code. Now, what I used for this demo, the device you can see here, and that little chip in the very middle is the ARM CPU and the FPGA. It's, by the way, called the Zinc, and it's manufactured by the biggest FPGA manufacturer, Xilinx, which is now AMD because AMD acquired it. Yeah, so that's the FPGA AMD FPGA ARM chip, and that smaller thing on the previous picture goes into this larger thing, which is kind of a motherboard that you can use for development. But this is only necessary indeed for development. So when it's on board of a satellite or something, then only the small thing is used. And let me now show you what Hastlayer actually creates and how that hardware is built up that we have created from our parallel algorithm sample, because that might be something cool as well. So now I'm opening Notepad++ to show you some more code. And what you see here is code, but it's not a program. This is some hardware code. This is actually the hardware code that Hastlayer generates. It's written in a language called VHDL. And if you scroll down a little bit, it actually looks a bit familiar because there's something called a function. There's also begin, if, else. It looks a bit like some basic kind of language, but it really isn't. There are similarities between hardware description languages like VHDL and programming languages like BASIC, but it's all surface level. Really, they are fundamentally different because all of this code you see here will be turned into a piece of logic hardware. It won't be executed on a processor. It will be hardware itself. And there's a lot of setup here and some library functions. But what's interesting is that if we scroll down a little bit more, we will see something familiar. There's something here that has parallel algorithm in the name. Now, that's actually something to do with our parallel algorithm sample. What you see here is this block. These are type declarations. This is not logic yet, but these are something, like variable declarations or a property declaration just in VHDL. These are variable declarations for our parallel algorithm class. And what's interesting here is that it has the index 0. And if you scroll down, we see exactly the same thing, but the index 1. And then again with the index 2. Now you may have a hunch about where I'm going with this. If you scroll down a bit more, we have the same thing again with index 247. And if we scroll down a little bit more, we see the last one of these with index 259. Now remember that in our C# class, we started 260 tasks. Now, those 260 tasks were taken by Hastlayer, and it created 260 copies of our algorithm. It created something like 260 little processing cores on the hardware. And that's what you see here. Again, these are just the type declarations, but the actual logic is a bit down. But this is like a 100,000 line long code file, so it's a bit inconvenient to just scroll around. But that's also there. We have pretty much 260 copies of that task on the FPGA, and that's where the performance advantages come from, because this is like having a 260 core processor just for this parallelogram class. It can be much faster than a CPU that consumes a lot more power. Now, it's hard to compare because when it comes to comparing a CPU and an FPGA, it's always apples with oranges. They're very, very different devices. But still, you can compare on the costs, you can compare on power consumption and operating costs, and you can also compare on performance, simply when you need that raw performance, the raw low latency, like it is the case with algorithmic trading. There, nothing else matters, just latency. And in such use cases, FPGAs can offer you a very unique benefit. And that, as a .NET developer, you can quite easily utilize with your existing knowledge. Now, a couple of closing remarks. By the way, what Hastlayer supports is a framework called Xilinx Vitis. You can think of this as kind of .NET for FPGAs, because the issue with FPGAs is that since it's low-level hardware development, the hardware design you create, the hardware design that Hastlayer generates, needs to support each FPGA individually. You can't just take the same code and configure another FPGA with it. You have to know what FPGA you target. Vitis makes this a little bit easier. It doesn't solve the problem completely, but it makes it easier. And because of this, Hastlayer can target a lot of FPGAs already, or it can target even new ones with some feasibly low level of effort. And these FPGAs include, onboard computers like this one that you can launch into space or put on board of drones. But it also includes some very high performance cards as well. They call them data center accelerator cards. And these are available in pretty much all major cloud providers. So Azure, AWS, Baidu Cloud, those all have these cards. And these are also widely used in the aerospace industry. So again, if you would like to code something that goes into space, as a .NET developer, this is your chance to do it. We have also done some benchmarking, and the details of these are again up on GitHub, so you can check out all the codes, all the details of how we did the benchmarking, what hardware we used, everything else. And these are the numbers that we got. Hastlayer is not uniformly better. It highly depends on the hardware you are using and your application. But to give you an idea, when using those high-performance accelerator cards, these are the speed and power efficiency increases that we have seen there for different sample algorithms. There's an image contrast modifier sample that was really good here, and the parallel algorithm that you already know was just about 4 times faster, but used about a quarter of the power, a 25th of the power. What we are comparing here is this such a high performance FPGA and the also high performance CPU in that virtual machine. Now, when it comes to the Zinc, so what I've used for the demo here, then there we are comparing the FPGA of the Zinc chip to the CPU of the Zinc chip. So again, apples with oranges, but at least we are comparing devices that are in the same ballpark. Now, the numbers here are even better. So two or even one or two orders of magnitude better performance and better power consumption here. We also have support for a number format called posits. Now, when it comes to working with fractions, probably you don't really think much about them because you just use double in .NET, or perhaps float if you want to be careful, or perhaps decimal if you are working with money. But pretty much that's about it. Now, that's fine, and that's what we use day to day, but there's actually a whole world of number types out there that in some way are better than the floats and doubles that we use in .NET, because these are some 30 or 40-year-old standards and following an IEEE standard. Now, there's a number type called POSIT that promises to be better than doubles and floats. It offers better range and at the same time better accuracy with the same amount of bits. And yeah, it's an interesting research area. We also created a .NET library that allows you to use POSIT numbers in any .NET software. What's the most interesting here is that it's also Hastlayer-compatible, and you can turn it into a piece of hardware. So that means that with Hastlayer, you can create your own number type, and then you can create a processor for your number type at the same time. Now, how cool is that? We are working on more use cases for Hastlayer. So if you have any use case where high performance is paramount, please let me know. We can work with you to figure out whether Hastlayer would help your use case. We are also partnering with the Wigner Research Center for Physics, which is well, all about theoretical and theoretical physics and applied physics. And of course, they do a lot of computations. So FPGA computations can be interesting there. And again, as mentioned, FPGAs are pretty much available in every public data center now. So I highly encourage you to check out what options you have. As mentioned, all the major clouds also have FPGAs. And the CPU manufacturers also know that FPGAs are useful because Intel, a couple of years ago, bought the then second largest FPGA manufacturer called Altera, and as I mentioned, AMD bought Xilinx. Now, to wrap up, if you like this, and I really hope you did, then please check out the SDK. It's up on GitHub. Everything related to Hastlayer is open source. And be ready, because I think FPGAs are coming. Because, you know, Moore's law won't go on forever. We are bumping into physical limits nowadays when it comes to CPU design. So transistors can't get much smaller nowadays. CPUs can't have higher frequency. When it comes to the architecture, then there's certainly room for improvement, but not too much. And dies, silicon dies, the chips are at their physical limits when it comes to the area as well. Well, the feasible physical limits. So we can't just put more cores onto a CPU. Now, what will save us here is heterogeneous computing. And of course, that's not a new thing. So we have GPUs for what, 2 decades now, probably, even more. And heterogeneous computing in general is, of course, a very, very old concept, even before that. Now, it's even more interesting, because even when it comes to some other computing than graphics computing, then using other processors makes sense. And of course, we also see that with AI. So we also have AI accelerators frequently available also in the cloud. So that was it. Thank you very much for your attention. If you'd like to get in touch with me, Here are my contacts. And again, all the code is up on GitHub. So check it out if you like to see some magic. Thank you.
Hey, thank you, Zoltán. If you have any questions, feel free to chat. Throw it in the chat. And I do have one question there. Give me one moment. Are you able to see the question, or you want me to read
it? I can't see it. Please read it. Yeah.
Okay. Are there any limits in the supported FPGAs, like number of logic units or RAM?
Yes, certainly. Unfortunately, there's no easy answer for that. So it's not easy to tell whether your algorithm will fit on an FPGA, apart from trying it. Luckily, you don't need to actually have an FPGA for that, because something that I haven't shown you is that when Hastlayer generates that hardware code, that VHDL code, with all the para-algorithm copies, then comes also some kind of a hardware compilation step. That's done by the FPGA manufacturer's toolbox or tool chain, and that will also tell you whether your logic will fit. Now, when it comes to the bare hardware resources of an FPGA, this varies a lot. This FPGA here, for example, it doesn't have any custom RAM because it shares the RAM, the memory, with the CPU. It does have a lot of little building blocks that you can configure to have the logic implemented there. And it also has something called distributed RAM, which are little pieces of memory scattered all around the chip. That's, for example, used if you have an array. So if in your code you have an array, that will be turned into pieces of memory on the FPGA, because there will be no dynamic memory allocation like it happens in .NET with the garbage collector. Now, for other FPGAs, the hardware can be much more complex as well. Have a lot more FPGA fabric, a lot more space for your custom logic, a lot more distributed RAM. There can be also little cores that do specific computations, like called DSPs, that can, for example, do multiplication of integers or even floating point numbers. And FPGAs can also be paired together on the same board with high bandwidth memory, with gigabytes, tens of gigabytes of high bandwidth memory. That's a lot faster than standard RAM in a PC. I hope that answers the question. Bala, are you here? Perhaps there's some issue with our connection. Let me check into StreamYard. And about the comments, if you can still hear me.
Oh, sorry, I was talking on mute. Sorry about that. Any details on hosting on ML model via Hastlayer? Any limitations on data in or out? Better to target the hardware like TPUs.
Yeah, great question. That's an interesting topic that we eventually want to check out, but we haven't yet. So we don't have an answer for that. If your model is specifically supported by a hardware accelerator like a TPU, then most possibly that will be the winning move. That will provide you with the most performance, because, well, FPGAs are fast, but baked in hardware is even faster. So FPGAs are kind of in between being software, being easy to modify as software, and being fast as bare metal chips. Because, well, a next step can be to actually manufacture that chip of yours, what Google did with TPUs, because you can have ML accelerators with FPGAs, and if you really want to go hardcore and you have millions of dollars to spare, then you can also manufacture these chips directly.
Thank you. I think I don't have any more questions in the queue.
Yeah, one audience member mentioned that they have a couple of FPGAs lying around. Well, you are certainly unique among the .NET community. But yes, please check out Hastlayer. You can also, by the way, add support for other FPGAs. So that part is also open source. Because again, Hastlayer needs to support each FPGA. Although with the mentioned Xilinx Vitis framework, it's a bit easier to add support than before, or than without it. In any case, if you have a Xilinx or AMD FPGA that's relatively recent and not too small, then most possibly Hastlayer either supports it or it can be made to support it quite easily.
Okay. Okay, Zoltán, thank you very much for taking your time, and thanks everybody for joining us today. See you next time with another topic. Thank you all for joining.
Bye, Ram.